Hi everyone. So the problem I solved here is a particle that is confined to live on a cone using Hamiltonian mechanics. And so if you look, you have a cone that is pointed directly upwards, gravity going down, and we have a particle at angle phi, which is swept out from the x-axis. Anyway, first step, you write your kinetic energy, which is 1/2 m rho dot squared plus rho phi dot squared plus z dot squared. So this is the radial direction, this is more of an angular direction, and this is the vertical direction. And the problem gave that rho changes with z by some constant factor, linearly with some constant factor. And so you plug that in, and some algebra brings you here. So this is the form of the kinetic energy in terms of two independent coordinates, z and phi. And then you also have your potential energy, which is mgz. And first step you do, you find your p's, your generalized momenta. Generalized momenta pz is equal to the partial of kinetic energy with z dot, which is equal to this. So basically, you're looking at this term. The 2 comes over, cancels out with the 1/2. You have an m c squared plus 1, and then a z dot left, which is your generalized z momenta. Generalized phi momenta is the same idea. Derive it with phi dot. This time you're looking at this term. The 2 comes over, you have an m, and you still have your... Sorry about that. Still have your c squared z and a single phi dot left, which is right here. And then you write your generalized coordinates in terms of your momenta. So the first equation gives you z dot equals pz over m times c squared plus 1. Phi dot is equal to p phi divided by mc squared z squared. Then your next step is you write this value, t plus u, kinetic energy plus potential energy, in terms of your p's and your q's. First, I wrote it in z dot, phi dot, which is basically just adding together this equation and this equation. And then I subbed in values for z dot and phi dot using these values here. Plugged it in. This is the value for the Hamiltonian. Then your next step is you write your Hamiltonian equations, which the general form is q dot is equal to the partial of Hamiltonian with p sub q, with p of that coordinate. And so my z dot is equal to derivative of Hamiltonian with pz, which, looking at this term, gives you just this. 2 comes out, cancels with the 1/2. You have an m on the top, 2 m's on the bottom, you have an m squared, m on the bottom, and then you have a c squared plus 1 on the bottom. And then your generalized momentum derivative, so your generalized force here, pz dot, is equal to negative the partial of Hamiltonian with that coordinate. And so that, for this term, we're looking at this and this, which is just equal to this. Just some basic calculus there. And then phi dot, same idea, derive Hamiltonian here with p phi, which is just this term, giving you this. And then we have no dependence on phi, so our p phi dot is equal to 0. What this means is angular momentum is conserved in a system like this. Moving forward, so the idea of solving these equations usually is getting something in terms of something along the lines of f equals ma, where a is the second time derivative of some coordinate. And so our two coordinates here are, sorry about that, z and phi. So z double dot, which is just the derivative of this one here, is just this. And we have our value for pz dot, which is this. So you have, plug everything in, you come here, which keeps getting more and more nastiness. Just for completion, I did the same idea for phi double dot right over here. So what we had on the other page was phi dot is equal to p phi divided by mc squared z squared. And then so you derive that, so that gives you some quotient rule calculus there. We saw on the other page the angular momentum's conserved, so this term goes to 0. Then you just have these two, which gets a little interesting, but still not very solvable because you still have this z thing here. So essentially what you get is two differential equations which depend on each other. So you have a coupled system of differential equations, but they're not even fun because you have z cubed terms here and phi dots and stuff, so it's not very solvable or intuitive.